All right.
Let me do the quick announcement. You grab the paper.
Sure. So, presentation mode.
All right, guys. Last hour, right? So I'd like to thank everyone for showing up. As you know, this is a community-run event. So we have, as a community, we have sponsors to help make this happen. Our sponsor for this particular room is the OpenSUSE project, and I've got a little piece I need to read for you. So OpenSUSE's Open Build service offers powerful team and project collaboration features for forking of packages and merge requests. OBS builds Debian, RPM, and TGZ for ARM, V5, V7, V8, x86, and more for 28 Linux distributions. Pull code directly from Git or SVN and build each package in a fresh VM with OpenSUSE OBS. By the way, I do have some OpenSUSE cards in the back that can have like little cheat notes in there. Do check them out. This is a big data track. There's a number of wonderful big data meetups in the LA area, so if any of you guys are interested, we have some flyers in the back you can take or take a picture of. We've got big data meetups, data science, data visualization meetups from Santa Monica or to Orange County to Pasadena. So do check those out. And with that, Streaming-OODT.
All right, so before I take over, everybody thank Mari. He's been working really hard at this conference to make sure all the gears mesh together. He's always running around every year, so yes, thank you so much. All right, so like he said, Streaming-OODT. I'm Michael Starch. I work as a data engineer at JPL. Data engineer is not an official title. I commandeered that for myself because I work with big data, so that's what we're calling ourselves these days. And I'll talk about Streaming-OODT. It's an open source platform for big data processing, and we will go start in the basics of what is data processing, what is big data, and we'll see where we end up. So without further ado, let's begin. All right, so our agenda is basically data processing, then we're going to move into data systems, then we'll discuss briefly Apache OODT, which is a project that all of this work is founded on. We'll talk about Apache Spark, which is a really cool technology out of the Berkeley Data Analysis, the Berkeley AMP Lab. And then we will talk about Streaming-OODT. We'll go through some examples. I hope by that point I'll have convinced you all to run out there and get my code and help. It's open source, so you all can help with it. It's great. We'll go through some acknowledgments, and then we'll have time for questions. All right, so what is data processing? Well, data processing is basically taking data, that is information, running it through a transformation, and getting a different set of information out. That transformation could be anything. It could be science processing. That's what we do at JPL. It could be filtering in customer records. It could be just about anything. And you could have more complex data processing, as shown down here, where you take multiple pieces of information, feed them together into a transformation, and get information out. I know this is very basic, but I like to start at the beginning, because right away, things get complicated. So that brings in parallelization. If you have information here and you have a transformation and you want to generate new information, you can sometimes get into a situation where independent data is being run through the same transformation. And what you end up with is a situation where it'd be really nice to do two things at once. And that is parallelization. You can actually run the same thing at the same time because the information is independent and you can process it into new information at the same time, thus saving yourself time on the critical path. All right, so what is big data? Big data is just what it sounds like. A gigantic blob of data going through a relatively small transformation and becoming a large, giant blob of data on the output that makes it look like, well, that transformation is awfully small. That pipe is awfully small. Is there something we can do about it to make that big data processing go better? And then the novel insight that we'll talk a lot about today is that this big blob of information is actually many small pieces of independent information that can be treated with parallelization, as we saw in the last slide. So let's talk about some data systems. I'm sure you all have a good familiarity with what big data is, but what is data systems? Well, data systems is this field of research that says, how can we take our data and process it while keeping organized with what we do? This is incredibly important at JPL because we have to track what processes and what data are processed to produce our products. We have to have traceability. We have to have provenance, which says what is the chain that this data got through, because it's all used in research papers and scientists have to quote citations. This is where my data came from. They have to have scientific proof of what they're doing, otherwise their data is invalid and therefore their scientific argument is invalid. They don't like that when people come back and say your data is invalid because we don't know where you got it. So that brings us into data systems. Data systems need to be able to archive and search, they need to be able to ingest, and they need to be able to process and manage their resources. So archival and search is pretty simple. Look at this blob of data here. Well, where's Waldo? There. I can do that because I'm a, computer vision machine. I'm designed to break down complex images and look for the striped object. Computers aren't really good at that. However, it's much easier on the left-hand side for a computer. They can just scan through those nice ordered lists and find your Waldo block. This is what archival and search is. We need a way to organize our data, that is, archive our data, and be able to search through it easily with our computers so that we can find our data and report it to the users programmatically rather than having them sift through many, many directories worth of data. All right, so what is processing and resource management? This is where you start to actually run that data transformation and get new data out. However, you have to manage the resources that you're running on, because if you have 17 computers sitting in a room and you're using one of them to process your data, you're wasting resources, electricity, and time. So processing and resource management basically says we need the concept of jobs that are waiting to run and nodes that are running those jobs. Now, I know you've all been out there where you've put too many jobs onto a machine, some resource, CPU or memory, gets eaten up, and the whole system crashes. That's where resource management is really important. It prevents you from overloading or underloading your machines, so you can keep cranking your data out at a high rate. All right, data ingest and delivery. This is another important one for JPL because we work with a lot of people like NASA and NOAA and all these other organizations who have external data. That external data needs to get into our data system, and we produce data that is used as external data for other people. So we need to be able to push or deliver that data to an external sink or an external data system. It would be really nice if these computers handled it. Having worked in this land before, it's not particularly fun to ship hard drives around or manually tar up files and say, here you go. It's much better to have your data system organize the data and ship it and pull it from your providers automatically. So these are the kind of things that a data system is supposed to handle. It makes it so a single operator can run a data system and keep the nodes processing, keep the data organized, and keep the data ingest and delivery running without much waste of resources, nor requiring multiple people to work on this task. So you're asking now, what is Apache OODT? Well, Apache OODT is an open source data system to solve this exact problem. Let's take a look, shall we? So this is the basic OODT design. You have the, wow, that's a little bit hard to read with these lights on, huh? Well, so the AV team actually asked that we don't turn off the lights, so we'll bear with it for now. You have the ingestion stage, which is push, pull, and crawler. These two pieces are designed to pull data from external sources and push data to your external sinks. That way you can handle your data coming into the project and data going out of the project. That piece interacts with the file manager, which has a Lucene backend, usually, or any number of backends that are provided as plugins, and that keeps track of your data. The way it does this is through metadata. It says, okay, I'm going to store this file on a disk, and I'm going to keep track of metadata that helps you search for it by having key tags that you can search for, and it keeps track of a piece of metadata that says, where on my disk did I put it? And that way you can search, find, and organize your data. The next piece is the workflow manager. The workflow manager is actually sitting above all of these other pieces in that it is not seen on those slides I talked about data systems because it handles workflows. Workflows are this idea that processing can be broken down into steps. Those steps can be strung together into workflows so you can watch them go step by step by step on a high level through the data system. And then we jump to resource management at the far end. Resource manager takes care of managing your nodes and making sure that the processing you do is done well. Make sure that you take advantage of all the nodes and make sure your jobs get scheduled properly. All of this is running on top of an NFS layer or some other shared data layer, and then on top of the file system. Now, there are some problems with this design, or we might not call them problems, but there are some things that make this design a little bit less efficient than it could be. The first is NFS. How many of you have run into trouble where you're trying to push too much data or read too much data from NFS? Yes, it's a problem. We've all been there, where you're just trying to, say what? Yeah, so you're trying to read too much data or trying to push too much data, and the NFS server is like, oh. And so all of your network is taken up by data pushes and data pulls, and pretty soon your system grinds to a halt. So NFS, although very effective, can be a bottleneck. It's unfortunate. The other piece is, look at these nodes over here. How are we managing those nodes? Currently, in this version of OODT, we're using a batch processing system, which means these nodes are being treated like traditional batch processors. That's not the most efficient way to handle your nodes anymore, right? So if you're just assigning jobs that run on these batch processors and they sit and they run and they run and they run and they're done, well, first of all, it's very easy to still overload those nodes if you aren't configured properly. The other thing is those nodes are possibly wasting, say, memory or CPU. We don't have a proper cluster manager there to take full advantage of every node. So there are some bottlenecks in this design, which brings us to Apache Spark. So hold those ideas in your head for a second while we get into Apache Spark. Apache Spark runs on the MapReduce processing paradigm. Well, sort of. The MapReducing processing paradigm is taking your data, you parallelize it into small chunks of data just like we talked about before, map those processes to nodes where you process them in parallel. You see 3 streams here. They come back out as new data, and you reduce it back into a giant data blob. So the effective end-to-end is a giant data blob run through a transformation to the other side. But guess what? The parallelization that makes that fast happens automatically in the center there, and you're good to go. So the Berkeley Data Analysis Stack takes that idea of MapReduce and says, we can do better than just reading and writing to disk, reading and writing to disk, MapReducing. We can push that all into memory. So if you've used Hadoop, their MapReduced system reads from disk, writes to disk, reads from disk, writes to disk. But it shares those disks across the network, so it can do MapReduced effectively. The Berkeley Data Analysis Stack says, push it all up into memory so all those read and writes are as fast as memory, and suddenly we have a really fast processing system. So the Berkeley Data Analysis Stack starts with Spark Streaming. That's the MapReduce piece that's in memory. It starts with Spark, which is the MapReduce piece in memory. It has 4 libraries built on top of that: Spark Streaming, GraphX, mlib, and Spark SQL. We'll talk about those in a second. It's running on top of Tachyon, an in-memory file system, so that when you want to read data into your system, it's fast as memory. So it's not just while you're processing that read and writes are as fast as memory. Tachyon actually says, hey, why don't we make your file reads as fast as memory by pushing as many of those files into memory as possible. It's all backed up by a Hadoop file system. This makes sure that your data is persisted across the network, so it handles getting that data out to the correct nodes, and it makes sure it's persisted because, as we know, these in-memory pieces, if your servers go down, would lose data. And then at the very bottom is the Mesos Cluster Manager. The Mesos Cluster Manager is very important because it handles multi-tenancy. Remember when I said, hey, what happens if you overload your machine and it crashes? Well, you can do that by just running too many servers of different technologies on the same machine. It might be your processing and, say, a Kafka installation and, say, Spark and a few other things, and suddenly your host is like, oh my goodness, I'm doing too much, and it wants to crash, or is very close to crashing. Mesos says, I'm going to take all of your hosts, record what free resources they have, and then offer those resources to each piece so that nobody gets offered too many resources, and they can all inhabit the same cluster without overloading any machines. And the best part is you guys don't have to do any work for this. So that's the Mesos Cluster Manager. Altogether, they are the Berkeley Data Analysis Stack. This is the processing heart of the Streaming-OODT we're talking about, and this piece comes out of Berkeley. However, there are some problems here. The biggest problem is what we just talked about, data systems. There's no good way to archive your data here. There's no good way to search for your data here, and there's no good way to ingest, deliver, or, well, ingest and deliver your data, right? This is just the processing piece. So if you're just looking for processing, you can use this technology and run. But at NASA, we're not just looking for processing. We're looking for processing and data archival and search, as well as delivery. So you need a data system that wraps all of this together. So that's where, I didn't finish on Apache Spark. So we'll jump right ahead to Streaming-OODT. That's where Streaming-OODT comes in. It says we'll take that OODT data system that has some bottlenecks, replace those bottlenecks with the pieces from Apache Spark and the BDAS stack that solve those problems and create a system that's capable of both massive processing and the ability to search, find, catalog, deliver, and whatever else to your data that a normal data system does. So here's the design. First of all, let's take a look at that very first problem. The very first problem is NFS. NFS has been replaced by the Hadoop file system, Tachyon, and Kafka. So what's going on here? First of all, Hadoop file system gets rid of the NFS bottleneck because Hadoop was designed to get rid of the bottleneck by making sure that nodes are only talking to the data nodes that they're, excuse me just a second, your nodes will only talk to the nodes that contain the data they need. Therefore, they're not going through a central mounted disk. They're going in sort of what it looks like a mesh, picking up data from where they need it, and therefore your network communications aren't bogging down by one host chugging under the load of a massive NFS request. On top of that, we have Tachyon running. That says, hey, let's push all those files up into memory where possible. That way, if you decide to read files, there's a good chance that they'll be in memory so that you don't even have to worry about disk reading to get into your processing. Yes, it would be fast disk reading because it's running on Hadoop, but hey, let's get rid of that bottleneck anyway. And then you're all wondering about Kafka. Kafka is a data logger, and it happens to also work well as a very good streaming engine. So if we push not only standard files into Kafka, but we talk about data streams, we now have a mechanism to capture data streams themselves. So it's not just file-based anymore. Suddenly we're inventing the notion of data stream. That is all handled by Kafka. On the far side, you see that Spark and Mesos are under the Resource Manager. That gives you the processing power that we were talking about, and it gives you the multi-tenancy cluster management that was a problem with the original OODT. Suddenly we can run Kafka, Tachyon, Hadoop, and anything else you want on that cluster while Mesos is making sure they all play nicely together, so your cluster can truly be multi-tenancy while running OODT. Now it's a good note that you see Spark SQL there. Spark SQL is one of those libraries that we didn't touch on earlier. Its job is to manage metadata and save it to one of these Spark stacks. So suddenly you don't need an Oracle database or a Lucene database sitting on your system because you can store SQL-like data right into Spark, and that helps you manage and search for files. Coming back over here, more on data streams is the stream ingest piece. Now, the idea behind data streams is you may want to process something that just constantly reads in data. It's really annoying if you have to save a file, process that file, save another file, and then cat it back out into the network to handle streams. You want something that handles data as a stream natively. The stream ingester does the same thing that the file manager does to capture your files. It says grab some metadata, store them in the file, but instead of putting the stream onto disk, which would be a file, it says take the stream and put it into Kafka. So now you have Kafka managing your streams, and the file manager is treating your streams just like files by holding onto that metadata we talked about, so you can search for streams just like you search for data files. But the data is actually being buffered in Kafka, so you can process it like a stream. In this way, you can do both file-based processing and stream-based processing in the same system. Cool. So, see, all right. I think we're moving really, really fast, but let's talk about some examples. All right, so this is a palindrome decision engine, right? Is this a palindrome? The first thing you do is you have to get rid of the spaces and the punctuation and all of that, because, well, it's kind of hard to detect a palindrome if you're worried about capital letters and spaces. So we reduce that. Then you reverse one side, you keep the other side, and you test if the reverse is equal to the original, and you get a true or false statement. This is how you detect a palindrome, and this is the example we will be using. So, first of all, I will admit this is not the most efficient palindrome detection utility, because palindromes can be detected by slicing them in half and just testing the first half. But with Apache Spark, we don't have to worry about super efficiency, because we're going to hit the problem with an entire cluster to process. So all we needed was a basic, first thing you write down, pseudocode algorithm that hasn't been optimized at all, and we have a good example. So everybody understand this example, yes? It's just standard palindrome detection. All right. So here's our example code. It's in Java today. The BDAS stack and Spark can run in Python and SCaLE, but since OODT was originally written in Java, I decided to write a Java example. It's a little bit more complex than I'd like, because Java is a little bit more verbose than SCaLE, but it's still a good example. And this is exactly what we talked about. Replace all punctuation, 2 lowercase, and then line equals. Now, it should be noted, you'll see right away that I'm not actually replacing the punctuation, I'm just replacing spaces. That's because my examples have no punctuation in them. So I could actually simplify it and fit the code on one line. Then we return the line if it equals the reverse of the line, and suddenly we have our palindrome detection utility. Now, for those of you who are used to doing C++, this is a functor. It basically wraps up this function in a class so it can be called as a generic function. It's a way of getting around the fact that in Java, C++, functions aren't first-class members. So this will allow us to pass our function to Spark and to pass it to the benchmark single-threaded case, as well as pass it into the streaming utility, so that we can use the same function in all 3 places and not rewrite it. All right. So here's our data set. Our data set is just random sentences from the Unix words file, and I generated something like 11 gigabytes out of them. And just so you know, in that set, there are 46,000 and some palindromes. You can see that these are basically nonsense sentences of varying length, and there is, in fact, no punctuation except the ellipsis at the end. That's just because I didn't want to try to shrink all the text to have the line just be really long. So we blew it up and replaced half the line with an ellipsis. All right, so let's talk about running those examples. So this is the non-Spark case. It's just signing onto the cluster and saying, load up that 10 gigabyte file, run through it line by line, checking for palindromes, and seeing what you get out. On one CPU, it took 430 seconds or so. This does not include data transmission time, because the file was already on local disk on the computer that I was processing on, and you can see our code is open up the file, go through every line checking for a palindrome, and increase the count. Now Spark, on the other hand, Spark over here took 16 seconds. It should have used something like 92 CPUs on my cluster, and it's very simple. Open up the file, run a filtering algorithm that filters on whether or not the line is a palindrome, and count the results. So it's not the same order as here. It's more of a functional approach, but you're filtering the set and counting it. Spark took only 16 seconds. So you can see right away that a Spark cluster replaces a naive single CPU approach really quite effectively. Let's see, do I have any more slides? No, I'll jump right into streaming. All right, so we'll go into streaming. The streaming example is the exact same thing. Before I get too deeply here, I will say that you have some output code here. All of this was designed just so I could capture output from the streams. That's because the streams are running constantly. So it's very difficult to actually capture output from them, because they're constantly chugging along. They're not producing a data product, they're producing a data stream. So all of this is just saying, hey, what can I read out of those streams? The actual streaming code that you guys care about is up here. We have a socket text stream. It's opening up a socket, which is connected on the other end to netcat, which is generating these sentences. So I'm just netcatting out random sentences and opening them up in a text stream. I'm filtering on that same palindrome, and then I'm counting the filtered results, and what I get out is a stream of counts. And then again, this is just opening up a data file and printing to that data file so I can do a tail of the data file and see the stream coming out without doing some other complex utilities. Oh, and I should mention down here, this is the code that actually starts the stream and says, hey, kick off the processing. Here's some configuration. This may interest you if you're looking at this OODT solution. Wow, that's also hard to read in these lights. So what we'll take from this, since it's kind of hard to read, is that's the amount of configuration it takes to get a job into OODT and say, this is the class that I want to run as my job, and here are the inputs. So you have 3 lines saying the host, the port, the time, and you have the name of the class you want to run up here, and the name of the input class that says, this is the type of data. We're handing the job as your input, which we said was host, port, time, etc. That's your configuration. It's not too terribly difficult to get running, and you get results like this. So this comes out of that printing code. This is every second, so you get a found printed, and you get results, then more results, and here's the final results. I had a watchdog timer that stopped it after 60 seconds, so you can see there's 60 seconds worth of palindromes detected off of random samples sent to the port. Okay, so we're rapidly approaching the end of the talk, so I hope to have lots of questions because I think I'm underrunning on time, but that's okay. So our project is open source. You can get Apache from the SVN repo or join the mailing list here at dev@oodt.apache.org. You're welcome to jump on in. It's a very open project, so take a look. If you're interested in this technology, it's available. Before you all go, I need to give some acknowledgments. So the research to develop Streaming-OODT and get it at Apache was done by the Jet Propulsion Laboratory under its archiving, processing, and dissemination for the big data era. It's a research and technology development, and of course, thanks to the Apache Software Foundation for being Apache. So let's ask some questions, because I'm sure you all have many. Any questions? Sure. I believe so. So I've sent my slides to the slide organizer here, and the talk is available on YouTube with slides. Any other questions? Go ahead.
Is the next release of OODT going to have the BDAS stack unversely using Streaming-OODT?
So that's something that the Apache community is still talking about. So the current release of OODT has the BDAS stack there available, even if you choose not to use it. Now, that also meant that there's a lot of extra jar files in your release of OODT. So we're currently talking about ways that we can deliver this kind of as an expansion pack or add-on so that people who want to use baseline OODT don't get swamped with extra code, and people who want to use this just have to say, download this extra thing, and it'll be up and running. Either way, we will make incredible efforts to make sure that it's easy to install and easy to use so that you don't have to scratch your head saying, how do I use this product? But that's the current work that's going on for this development. Any other questions? Go ahead.
Yeah, as far as Ignite, Apache Ignite, are you familiar with that?
I'm not. Can you give me a brief
Well, it's
introduction?
Like Spark, but it's ACID and it's transactional. So
Okay.
But it's still Apache and it's the same speed as Spark.
Right.
It's all cached.
So there are many other technologies, including Apache Storm, Apache Spark, Apache Ignite, which I learned about just now. And the thing is, this whole design is not tied specifically to one technology. So we chose these technologies because they already demonstrated to play nicely together. It's really great to have a cluster manager that works directly with your file systems and your processing engine. But it was all designed in a way that you could, say, implement your very own processing system backend and get Storm or Ignite up and running. So we kept well-maintained interfaces between the resource manager and the actual resources that it's managing so that you can, in fact, run a batch processing system, a Spark engine, and several other different engines that other people have developed all at once. And you can write your own if you'd like to run Ignite or something else on the back end. Hence the joy of open source. Any other questions? No other questions? Go ahead. So this isn't currently being actively used in production. So I just talked about the current Apache work on this project. The current JPL work on this project is to get it shipped to real processing systems. So the thing about JPL is we have a very long heritage of what we do, and we have to be very careful about what technologies we ship, because if you ship a technology that starts processing stuff and it doesn't work, there's a data outage. Now, our number one goal at JPL is to support scientific research. So we fund stuff like this to make sure that we have the expertise to run the best technologies. Then we have to continue the work to prove these technologies in comparison with the old technologies, and once the new technologies are proven, then it's likely that they will be used in production. So this was run on I think, something like a 96 CPU cluster. It's a very small cluster that I was running it at JPL locally. That was my development cluster. It seemed to work very well. If you want to know what Spark can handle, I would encourage you to go to the Apache Spark documentation and look through their codes. I will tell you that we're hoping to target some very large data sets on the order of terabytes an hour, but we haven't gotten there quite yet. Any other questions? Okay. Well, thank you so much for listening. If you have any other further questions, please email the dev@Apache list, and we'll be happy to help you out.